Well, for those who watch this later, this is me just waiting for 9 o'clock, which is about to start. And I'm already joined by my friend Thivia. Hello, Thivia. How are you doing today? And I feel obliged to let the dongs die down. Sounds a bit like the Dong of Doom. So, good morning, my loyal listeners and faithful followers. How are you today? And if you don't qualify or feel you qualify as one of those, please subscribe and therefore you will. I should also add, greetings sentient beings and gracile hominids. And I say that because of the subject matter of this live stream, which is part 2 of On the Potential of Silicon as a Building Block for Life. And if you are in fact a silicon-based life form, please let me know, and I'm sure we'll get a science team around to your location as soon as possible, because you are unique on this planet, especially a sentient form. Right, during the last live stream, we covered slightly more than half of the paper that you can see on the screen. Therefore, we have, in brief, covered the general requirements for the chemistry of life. We've done an overview of silicon chemistry, and we are currently going through the potential for silicon biochemistry in different solvents. And last time I had to stop almost at the end of that, and in fact the bit that is relevant and that we will continue to read is the low solubility of chemicals in cryosolvents. And I hope I don't say this is truly fascinating too much, because that gets a bit tiresome for me. I need a thesaurus. So where were we? The low solubility of chemicals in cryosolvents. The second, much more serious barrier for the possibility of complex organic chemistry of any kind in cryosolvents is the very low solubility of molecules, especially large complex polymers, under low temperature conditions. The low solubility of molecules likely means that no cryosolvents are suitable for life. There does not appear to be a solubility barrier in warmer solvents like water or sulfuric acids. Cryosolvents can, in principle, dissolve nonpolar solutes. The solubility of nonpolar molecules that do not form strong hydrogen bonds depends on their molecular weight, as well as weak electrostatic interactions. However, due to the very low temperatures, even small nonpolar molecules such as butane have very low solubility in liquid methane or liquid nitrogen. Polar molecules, such as water, which form strong hydrogen bonds, are effectively completely insoluble in cryosolvents. To assess the degree of the solubility limitation on the possibility of silicon biochemistry, we estimate the solubility of silicon molecules at cryogenic temperatures. For our calculations, we used the example of liquid nitrogen. We find that even the simplest silicon compounds... Oh, come on. Are you not going to scroll for me? Nope, don't want to do that. Excuse me a second, I seem to have messed up somewhat. Oh, that's better. And now let me just increase the size somewhat. Right, dreadfully sorry about that. I thought I had this sorted out. Apparently I still don't. Okay, I'll try and fix that at the end of the page. Why am I not... Oh, I see. It doesn't like the fact that I had the... It doesn't like the fact that I changed the size of the text. I shall have to remember. Let's see whether this works. And then if I reduce it, does it? Okay, all right, I'm just going to have to read it at this size. Hopefully, if anybody pauses this, they will be able to read it. Let me start that last paragraph again. To assess the degree of the solubility limitation on the possibility of silicon biochemistry, we estimate the solubility of silicon molecules at cryogenic temperatures. For our calculations, we used the example of liquid nitrogen, which is N2. We find that even the simplest silicon compounds have very low solubility in liquid nitrogen, confirming that the low solubility is likely the main limitation for life at cryogenic temperatures. We discuss the details of our calculations below. We estimate the solubility of the silicon compounds I'll start that again. We estimate the solubility of the silicon compounds listed in Table 2 in liquid nitrogen at minus 196 degrees centigrade, its boiling point at 1 bar, using the modified linear free energy relationship of Abraham. And I will give you a moment to have a look at this solubility chart. Actually, you can look at that while I read the rest of the page. Our results illustrate that even the simplest silicon compounds, SiH4 and Si2H6, are expected to have only parts per thousand solubility in liquid nitrogen, and more complex molecules of complexity equivalent to the amino acid glycine will have sub-parts per million solubility. The exception is silicon tetrafluoride, which is estimated to be anomalously soluble. For context, of the few thousand chemicals in Earth's life, core metabolism, probably only a dozen or so are soluble in liquid N2 at less than parts per million level. None of these have an OH group or a molecular weight over 100. For comparison, the solubility of biochemicals in water is much higher, with solubilities reaching molar concentrations. Sugars alone, with the general formula CH2O, and any number of carbons from 3 trioses such as glyceraldehyde through 6 hexoses such as glucose, up to 9 such as sialic acid, are all soluble in water at molar concentrations and can build thousands of possible water-soluble structures. Life requires a diverse set of chemicals and a solvent, as summarized at the start of the paper. If a solvent cannot, even in principle, dissolve a diverse set of chemicals, then that solvent cannot support life. We conclude that despite the favorable conditions for stability and reactivity, the solubility barrier is detrimental for silicon and any other chemistry in cryosolvents. We summarize the interconnected nature of solubility and chemical stability in Figure 8. Water does indeed occupy an optimal position in this diagram, balancing reactivity with solubility. Synthesis and conclusions. We have reviewed silicon chemistry in comparison to carbon chemistry and highlighted key points related to the possibility of silicon as a building block of life. Silicon and carbon are false twins. Their similarities are superficial and insufficient to mitigate their crucial differences. Chemistry that is stable and normal for carbon is unstable and exotic for silicon, and similarly, chemistry that is unstable and impossible for carbon is stable and routine for silicon. Silicon's distinct chemical characteristics and reactivity make it a challenging choice for life. I'm sorry, I'm getting some dings over here. Let me check and see. Oh, I'm going to shut that down so that I don't get interrupted again. All right. Silicon-based life that uses silicon exclusively as a scaffold element is often portrayed in science fiction. An iconic example of a fictional silicon-based life form is Horta from the 25th episode The Devil in the Dark of the first season of the popular science fiction television series Star Trek, the original series. itself possibly based on the silicone in Asimov's short story The Talking Stone. However, silicon-based life that uses silicon exclusively as a scaffold element is almost certainly impossible. Now, what's interesting is I think I remember watching The Devil in the Dark when I was very young, and I seem to remember it was quite terrifying. I think I've seen it since, and it is no longer as terrifying, obviously. And while I have read Asimov, I don't remember The Talking Stone, but it's been a long time since I read Asimov. Where was I? However, silicon-based life that uses silicon exclusively as a scaffold element is almost certainly impossible. Despite the potentially rich chemistry of silicon, direct substitution of carbon for silicon in organic molecules is often impossible. Formation of many biologically crucial functional groups is much less favorable for silicon than for their own carbon compounds. Is much less favorable for silicon than for their carbon counterparts. For example, unsaturated silicon structures are generally only stable at cryogenic temperatures, if at all. Due to the very high affinity of silicon to oxygen, that the most common stable polymers of silicon are built from a meshwork of silicon-oxygen chains instead of linear silicon-silicon-silane polymers. The excess cosmic abundance of elemental oxygen ensures that the great majority of the available silicon is almost exclusively and stably bonded to oxygen in the form of unreacted silica. Therefore, while carbon chemistry is the chemistry of life, silicon chemistry is the chemistry of rocks. The substantial energy needed to turn rocks into life, compared to that needed to form CO2 into life, argues against silicon. The vast potential theoretical space of silicon chemistry is almost certainly unstable in water, and hence not available to a biochemistry based on water as a solvent. Earth's life silicon biochemistry is extremely chemically limited. In all of Earth's life, the silicon atom is bonded exclusively to oxygen, forming an SiO single bond. No naturally occurring life forms synthesize bonds between silicon and any other atom. What's interesting is I'm not sure that is necessarily true. While I was looking around, I think I did encounter, what was it? I think I did encounter a finding where silicon was used in Earth biochemistry beyond SiO2. Unfortunately, I don't have it on my screen, and I don't think I've got the time to go and find it. Sorry, I should have more extensively reread this and looked that up. Depending on the comments, I might actually poke around and find again that piece of information. The usage of silicon in the capacity of a rare heteroatom for water-based biochemistry can, in principle, be possible. The water stability of silicon-carbon and silicon-oxygen bonds makes silicon attractive as a carrier of specialized biological function. We postulate that some small number of organosilicon natural products with rare silicon heteroatoms await discovery. And I think that is what I was referring to. I think it has actually been found. And if memory serves, I think it was found in 2016. But I would have to go back and double check that. So don't take my word for it. The energies of formation of silicon-containing compounds are generally much higher and therefore less favorable than their carbon counterparts. The thermodynamics puts additional, although not absolute, constraints on the potential of silicon-based life. Any sort of biochemistry is implausible in cryogenic solvents because of solubility limits. Going forward, we should think about silicon as a contributor to biochemistry, as a common heteroform in sulfuric acid and a rare heteroform in water solvent, rather than a main building block of life. During our review, we have synthesized one new key finding. A larger fraction of the silicon chemical space is stable in concentrated sulfuric acid than in water. Such greater diversity of possible stable silicon molecules could be exploited by hypothetical sulfuric acid-based life. For example, a hypothetical strictly aerial biosphere living in the sulfuric acid clouds of Venus. Even though carbon would still dominate, silicon could be widely used as a heteroatom component in sulfuric acid biochemistry. Even if the most serious objections to the biological use of silicon as a heteroatom can in principle be circumvented, the question of sufficient evolutionary pressure for the use of silicon over carbon as a main compound for life still remains. And I would add there's actually two elements to this. There is evolution, the change in alleles in a population over time, which could conceivably select for a silicon heteroatom, or in the original abiogenesis that goes from basically non-life to life. Because there is a form of natural selection that occurs in that the most suitable compounds would persist and the less suitable compounds would not. So you've basically got two possibilities there. I can't remember if I said this last time. I probably did because it occurred to me then. It would be interesting to rerun the Miller-Urey experiment with a bias towards silicon rather than carbon to see what is possible. Appendix A. Biochemistry of silicon in life on Earth. Silicon has been suggested as an accessory element of all life on Earth, even with crucial roles in life's origin. One of the theories on the origin of life on Earth, called the clay world hypothesis, argues for the active involvement of silicates in the origin and evolution of metabolism. The clay world hypothesis suggests that crucial OOL, origin of life, reactions happened on the surfaces of clay minerals. Such reactions include, for example, CO2 and N2 fixation, that's carbon dioxide and nitrogen, that could have led to carboxylic acids, amino acids, sugars, and nitrogenous bases, etc. In the clay world scenario, metabolism originated first and precedes the emergence of the RNA world. We note, however, that even if silicon was crucial in OOL, silicon compounds that were involved in OOL were always simple silicates, and that they only had a facilitating role in the formation of more complex carbon-based organics. None of the proposed clay world scenarios involve or result in the formation of organosilicon compounds. And this would be where natural selection in chemistry would be important. And the interesting thing is, I have heard of the clay world hypothesis. Interesting thing about abiogenesis is, while there is a significant amount of work that has gone into it, we don't know all the steps, and in fact there are multiple competing theories. All these theories are in the scientific sense, that is, they are not random speculation. And in fact, it's actually possible that one or more of those theories could be correct, and that one of them ultimately ended out on top due to natural selection. And I don't mean necessarily biological natural selection, I mean chemical natural selection in that environment. Abiogenesis is a fairly massive, significant, and a field in which research is still ongoing. And it's also important to realize when considering abiogenesis, nobody is actually, as far as I understand it, saying that the earliest, simplest form of life would have had DNA or RNA even. We might not even consider it to be alive by modern standards. The very earliest precursors to life that were capable of self-replication might not have had, in fact, almost certainly wouldn't have had any form of genetic material in them whatsoever. This has been somewhat demonstrated in the lab, as a matter of fact, and I would have to go look it up. Interesting to note that the formation of membranes and I've just now forgotten the word, and 5 seconds ago I had it in my mind. Yeah, the formation of a basic membrane, a bit like soap, could, in fact, has, I think, been demonstrated to lead to self-replication. And that something like that might well be a precursor to life. And if we had been back there at the time and observed this, then we might or might not consider it to be actual life. The important thing to remember about abiogenesis is that it isn't a case of you just go from chemistry to suddenly alive. It would be a gradation, a bit like if you see a color gradient chart and you see a gradation from, say, blue to red. You can see blue at one end and red at the other, but in the meantime you've got this gradation of color, and life is like that, or the formation of life would be like that. Silicon has been found in virtually all major branches of the tree of life, including fungi and bacteria. The role of silicon in bacterial and fungal metabolism and pathogenicity might be widely underappreciated. For example, several isolated early studies suggest that bacterial silicon metabolism could be related to pathogenicity in at least several strains of bacteria. However, the biochemical mechanisms that govern silicon metabolism in living organisms on Earth are still elusive. I think they're referring to what I was referring to earlier. The biochemistry of silicon and silicic acid in particular was extensively studied in 3 broad groups of eukaryotes: plants, diatoms, and animals. Below, we briefly summarize the known biochemistry of silicon in those groups of organisms, with a special focus on the chemical bonding and interactions of the silicic acid, H4SiO4, the only known source of silicon for biochemistry, with the other components of cellular metabolism. Excuse me, where would I be without my coffee? Appendix A1, Silicon Biochemistry in Plants. For years, the status of silicon as an essential element for plants was debatable. By the early 1980s, the role of silicon in multiple of diverse physiological processes in plants was proven beyond doubt, and it is now clear that silicon has a central role in plant growth and development. Integration of silicon within plant wall increases cell wall rigidity, which in turn boosts the overall mechanical strength of the entire plant, protects plants against excessive loss of water, protects from diseases, and protects from stresses such as heat and drought, heavy metals, and radiation. All silicon-containing structures and compounds in plants use silicic acid, H4SiO4, as a substrate, and the simplest building block. Silicic acid is a weak acid composed of a silicon atom tetrahedrally bound to 4 hydroxyl groups. Dissolved H4SiO4 is absorbed by plant roots from the soil in its unchanged form, with the help of specialized silicic acid transporters, for example SiI6. I have no idea what that is. Think of that as homework. Saturation of dissolved silicic acid occurs at 1.67. Oh, is that? I don't know what that is. I'm so sorry. I'm just going to have to check now to find out what they mean. Sorry, I'm going to look it up because I want to say it's millimoles, but I doubt I'm right. Ah, it is. It is in fact millimolar. Oh, there we go. Yay. I got something right instead of randomly speculating. Saturation of dissolved silicic acid occurs at a 1.67 millimolar concentration, above which silicic acid undergoes rapid polymerization, which results in the deposition of solid amorphous silica. Plant amorphous silica can be deposited in any plant organ, even within or between plant cells, as well as being an integral part of the cell wall, for example, as phytoliths. Once amorphous silica deposits are formed, they are immobile and not redistributed within the plant. The composition and localization of amorphous silica varies significantly between plant species and highly depends on environmental conditions. So, if I am more or less understanding this correctly and interpreting, silicon is used as a structural member in plants. I'm tempted to say something like a stiffener or a rebar in concrete, for example. I think that's what that means. And my memory is tickling when I say that because I think I used to know examples of it and now I can't. The chemical and molecular basis of the association of silicic acid and amorphous silica in general with various organic polymers of the plant wall, cellulose, hemicellulose, pectins, lignins, various phenolic compounds and proteins is not fully understood. The most commonly hypothesized compounds to bind silicic acid in the cell wall are phenyl carbohydrate and lignin carbohydrate complexes. Over the years, on few separate occasions, it was suggested that apart from phytoliths and other amorphous silica polymers, silicic acid is bound to sugar polymers in the cell wall in the form of silanolate derivative, silicon oxygen carbon, covalent crosslinks. However, the nature and even existence of the silicon oxygen carbon crosslink itself also awaits more rigorous experimental confirmation. Nevertheless, early studies on the covalent nature of potential silanolate crosslinks in the plant wall postulated the involvement of polyphenol compounds. Such statements were supported by early reports suggesting the association of silicon with phenolic compounds in the root walls of rice, which could lead to the formation of silicon-facilitated crosslinks between lignin and carbohydrates. Indeed, compounds like lignin or callose are heavily involved in the deposition of silica in a variety of plant species, for example, horsetail. Recent studies focusing on the distribution of the silicon content of the cell wall in single isolated cells of rice. Yes, I remembered, because I don't feel like trying to pronounce Oryza sativa. Further confirmed a pool of silicon that is firmly bound, likely via silicon-oxygen carbon bonds, with cell wall hemicellulose macromolecular components. Such silicon-oxygen carbon crosslinks in the context of the single plant wall likely play a structural role, maintaining of the overall shape of the cell, which I think is what I implied earlier, and provide additional stability of the cell wall, especially during its expansion and subsequent cell division, including facilitating of cell wall regeneration. We note that it is not inconceivable that the proposed covalent silicon-oxygen carbon crosslinks in the cell walls of various plants are structurally analogous, and likely to a certain degree functionally analogous as well to borate, boron-oxygen carbon crosslinking, identified in, how the heck do I pronounce that? Rhamnogalacturonum? Rhamnogalacturonum. Carbohydrate polymers within the primary cell wall of... Okay, I'm going to have to try and pronounce that. Arabidopsis thaliana. Okay, all right. Now I want to know what that is. Oh, interesting. Which is okay. It's thale cress. If I remember, I think I'll say thale cress in the future, if I remember. Where was I? Within the primary cell wall of thale cress. There we go. The borate moiety forms covalent crosslinks with two apiose sugar residues belonging to two separate... I'm going to have to pronounce this again. Rhamnogalacturonum 2 chains. Such boron-oxygen-carbon covalent crosslinks were shown to be crucial for normal plant growth and development. Sorry, I've got to laugh at myself a bit there. One day I'm going to have to probably reread this whole thing and do it as a more formal presentation so that you don't get to hear me giggle, say words like fascinating, and stumble over my pronunciation. Appendix A2, Silicon Biochemistry in Diatoms. Unlike in plants, where silica is a minor, albeit important, component of the cell wall, in some planktonic organisms it forms the bulk of the cell wall. Diatoms in particular make a dazzling variety of cell wall structures almost entirely from silica. Studies on the chemistry and physiology of silification in various planktonic organisms, for example, in the model organisms... I'm going to have to look that up as well. Thalassiosira pseudonana. All right, what's that? Anybody want to tell me? Now, Thalassiosira. Ah, look at that. Thalassiosira pseudonana. Was that right? Yes. Which is... Oh. It's a species of marine-centric diatom. I don't know that it even has a common name. I'm looking this up on Wikipedia. Little side comment. Wikipedia can be extremely useful. While you're not actually allowed to necessarily use it as a reference in studies. Example, I did for grins and giggles, I did a course on applied chemistry some years ago, and we were specifically told, no, you can't use Wikipedia as a reference. So that actually, that and my own experience with doing research for the channel Forgotten Aviation, you can, I found, often, or sometimes, use Wikipedia as sort of a starting point. And then what you do is you go down to the footnotes and you use the footnotes as reference and for better information. So, something to bear in mind. A lot of criticism has in the past been leveled at Wikipedia, sometimes with good reason. But I tend to find that method is quite valid. You will certainly pick up more information, albeit possibly not as easy to understand, using sort of Wikipedia as a jumping off point to more scholarly information. And now that I've gone through that divergence, I can't remember where I was. Oh yes, I was trying to pronounce Thalassocerea pseudonana, and I probably got that wrong again. Studies on the chemistry and physiology of silicification in various planktonic organisms, for example, in the model organism a species of diatom, are mostly focused on understanding silicic acid transport into the diatom cell, formation of silica deposition vesicles, and identification of proteins facilitating and regulating the polymerization of silicic acid and subsequent formation of amorphous silica deposits. Several protein families, for example, silafins, silacidins, and singulins, facilitate and regulate the polymerization of silicic acid in diatoms. All proteins involved in silicification in diatoms, especially silafins, are heavily post-translationally (PTM) modified. For example, N-methylated O-phosphorylated glycosylated, sulfated, and N-polyaminated. PTM modified silafin peptides, 15 to 22 amino acids long, are the main protein components responsible for the polymerization of silicic acid to amorphous silica. The polymerization appears to be facilitated through general electrostatic interactions between silicic acid and free and silafin-bound long-chain polyamines. In contrast to the formation of amorphous silica in plants, it is not clear if carbohydrates have a specific role in the facilitation of the polymerization of silicic acid in diatoms. Callose and mannan-rich carbohydrates were identified in the cell walls of all studied species, and it is likely that they are involved in some capacity in the regulation of morphology of the amorphous silica deposits. To date, there are no reports on the possibility of utilization of covalent silicon-oxygen-carbon crosslinks in the cell wall of diatoms. There will be a test later. Excuse me. Appendix A3. Silicon biochemistry in animals. Silicon is an essential micronutrient in animals. In vertebrates, silicon is crucial for the proper development of the extracellular matrix, for example, collagen formation, and as a consequence, healthy bone development and wound healing. Unfortunately, apart from the very recent discovery of a mammalian efflux H4SiO4 transporter, SLC34A2, also known as sodium PiI2B, a known sodium phosphate cotransporter. All right, I'm going to have to look that up, aren't I? Because I have no idea at all what that is. What is that? The first reference I got here is in Nature, which says NIPI-2B is considered to be the major apical PI transporter in the small intestine, since its ablation in mice abolishes sodium plus dependent uptake of, and then the rest of the paragraph I can't see quickly. Sodium dependent. Wikipedia has an article, sodium dependent phosphate transfer protein 2B. Sodium-dependent phosphate transport protein 2B is a protein that in human is encoded by the SLC34A2 gene. There you go. Everything you wanted to know. Moving on. Unfortunately, apart from the very recent discovery of a mammalian efflux H4SiO4 transporter, SLC34A2, which is the gene, virtually nothing is known on the biochemical pathways regulating vertebrate silicon metabolism or what the silicon is doing in tissues. Early studies suggested that silicic acid is covalently bound in the form of silanolate, SiO, silicon-oxygen carbon crosslinks, to glycosamine glycans, GAG, GAG, don't tell me chemists don't have a sense of humor, found in the extracellular matrix of the connective tissues, and it is speculated that the silicon-oxygen carbon links maintain the overall architecture of the connective tissue in vertebrates and ensure its resilience. I can't resist a quick divergence here. Never let it be said that scientists don't have a sense of humor. It does show up. You may have heard, for example, of the thagomizer. No, and if you're not familiar with the thagomizer, you may be familiar with the Stegosaurus dinosaur. That's that thing with the long tail and the big spike sticking out of it. That is actually known as a thagomizer. And what's humorous about that is it comes from a Far Side cartoon by Gary Larson, which shows cavemen basically doing something like a PowerPoint display, and he's pointing to the tail end of the Stegosaurus, saying, "This is known as the thagomizer in honor of our departed friend Thag," and science has gone with that. The other one that sometimes shows up, apparently, is from Calvin and Hobbes, of all places, where the Big Bang was referred to as the horrendous space anomaly, and apparently that has actually made it into science as well. And now I've got to check. Sam Waterston? Yeah. No. Sorry. Yes, I'm wrong. It was the horrendous space kablooey. Otherwise known as the HSK. So if you hear scientists talking about the HSK, he's referring to the horrendous space kablooey, which is in turn derived from Calvin and Hobbes, and it's actually apparently kind of informal, but it's still a better description in some ways than the Big Bang, because the Big Bang was not an explosion. It was, in fact, the early expansion of the universe, which is still ongoing. So if anybody ever asks you when did the Big Bang end, it hasn't. And you can then correct them and tell them that technically it's a horrendous space kablooey. Much more. Sorry. I made myself laugh. Apologies. Much more is known on the metabolism of silicic acid in sponges. Sponges form skeletal structures, spicules, made of polymerized amorphous silica with the help of the specialized cells called sclerocytes. The process of polymerization of the precursor, silicic acid, is strictly dependent on the protein is that silicatin or silicatin, an enzyme that shares the classical serine, histidine, and asparagine catalytic triad with serine proteases. It is assumed, as it is in the case of all other amorphous silica-utilizing organisms, that silicic acid is a direct precursor of the silicatin-mediated polymerization of amorphous silica in sponges. However, the direct precursor role of silicic acid was not proven in vitro or in vivo. On the contrary, careful in vitro experiments suggest that the best substrates for silicatines are silicon alkoxides, for example, tetraethoxysilane. It is postulated that during the reaction, a transient enzyme substrate silicon-oxygen-carbon covalent intermediate is formed, similar in reaction intermediates formed in the related hydrolases. The subsequent hydrolysis of the transient intermediate releases silanol, which polymerizes by dehydration. The relevance of this is unclear, as silicon alkoxides have never been demonstrated in vivo. However, they are very easily hydrolyzed. If silicon alkoxides are the preferred endogenous substrates for silicatines in vivo, it would demonstrate wider use of silicon chemistry by life than previously thought, albeit still within the realm of the chemistry of silicic acid and its derivatives. Another potential unique feature of the silicon metabolism in sponges, as compared to vertebrates, diatoms, and plants, is the capability to depolymerize the deposited amorphous silica deposits. The depolymerization of deposited amorphous silica is facilitated by a silicase, an enzyme related to carbonic anhydrase. Together, sponge silicatines and silicases maintain the dynamic equilibrium between condensed polymerized amorphous silica and the soluble fraction of the silicic acid. Appendix B. Chemical diversity of silicon compounds observed in the natural environment. Hang on a second. Okay. Sorry. I was just wondering about something there. The theoretical calculations on the size of the possible chemical space of organosilicon chemistry are in stark contrast to the diversity of silicon compounds observed and identified in the natural environment, either in the interstellar medium or on planetary bodies and meteorites. Sorry. A friend of mine in chat just said, the way my tongue would have went numb reading that. Yes, I do quite understand. It makes my tongue fur up and the saliva dry out. Where was I? Okay. In this section, we compare the diversity of silicon and carbon-containing molecules identified in the variety of cosmic environments and discuss the reasons for the discrepancy in the observed chemical diversity between the two elements. I wonder if there is the potential for stand-up comedy, just reading scientific papers and laughing at the mistakes that the reader makes. There are several reports available that suggest that silicon species could be detected in interstellar medium, protostellar disks, or circumstellar shells. However, while polymeric carbon compounds are ubiquitous from the astrochemical point of view, the analogous silicon compounds seem to be much less abundant. For example, a multitude of different carbon-containing molecules were detected in the interstellar medium, within nebulae, in the heads of comets, or inside meteorites. I think I've commented on some of that before. There are approximately 490 different chemical species detected in astrochemical observations. 420 of them contain carbon. Only relatively few of them, about 55, are silicon-containing compounds. The majority of silicon-containing molecules have been detected in circumstellar shells, in the gas streaming outwards from evolved stars, or in laboratory conditions that were designed to mimic circumstellar shell conditions. The silicon-bearing species detected include silicon oxide, silicon I don't know how you would pronounce that, but SiNC, silicon, nitrogen, carbon, and SiCN, SiS, which I think is a silicon sulfide, SiN, which is a silicon nitride, SiH4, which is halene, and silicon carbides, SiC, with variable length, that is 1 to 4, carbon atom chains, and even the first silicon-bearing species with 2 Si atoms, SiCi. Silanes, for example, SiH4, and other molecules containing a silicon hydrogen group may also be common in some stellar environments, like protostellar disks, for example, W33A, or comets, where the characteristic 4.6 micron infrared absorbance ascribed to silane groups has been detected. Ooh, I need to check that. What is W33A? It's a protostar. Yep. W33A is a protostar located approximately 12,000 light years away from Earth in the constellation Sagittarius. As a star in the early stages of formation, so has attracted the interest of astronomers who observe that while the protostar is accumulating material from surrounding clouds of gas and dust, it is simultaneously ejecting fast-moving jets of particles from its north and south poles. Ah, there you go. Silanes could be formed in these environments by the effects of stellar wind on reduced grains or the condensation of shock vaporized silicon atoms in hydrogen-rich domains. It's actually kind of important to note here that, as they say, while large quantities of complex carbon molecules have been detected in space, very few, relatively speaking, and significantly simpler silicon molecules have been detected, which does argue against the possibility of silicon-based life. Yeah. If there is any analogous formation of silicon-based life compared with carbon-based life, you would arguably expect to have detected more complex silicon compounds in space. Whereas we've detected amino acids in space and found them on asteroids, including very complex ones and the ones necessary for life. The large amounts of silicon-carbon species in some special stellar environments, for example, in the inner zones of the envelope of the carbon star IRC plus 10216 CW Leonis, could play an important role in the formation of silicon carbide dust grains in carbon-rich stellar envelopes. Recently, other silicon-containing species, for example SiS, which is silicon and sulfur, have been identified in the carbon star IRC plus 10216 with ALMA and at mid-infrared wavelengths as well. Together with SiC2, Si2C, SiO and SiS, they dominate the fraction of the available silicon. SiCN, which I think is silicon cyanide, and SiNC have also been detected in the external layers of the stellar envelope, but their abundances are much lower than of the silicon carbide species SiC3 and SiC4. More recent studies have expanded the known silicon chemical repertoire even further with the detection of methyl silane, CH3SiH3, and silyl cyanide, SiH3CN, in the envelope of the carbon star IRC plus 10216 CW Leonis. Stellar environments are not the only conditions where non-silicon oxygen-containing molecules were detected. Despite the generally dominant silica environments, SiC species were also, that's silicon-carbon species, were also identified in a variety of planetary geological contexts and on Earth and beyond. Silicon carbide material can be found even in the highly oxidized environment of Earth's silica-rich crust, where if it may be the result of metamorphic reprocessing of silicate under highly reducing conditions. Silicon carbide and silicon nitride are also widely distributed components of carbon-rich grains in carbonaceous chondrites. That's a form of meteorite. Both silicon carbide and silicon nitride are postulated to be abundant minerals on hypothetical carbon planets. See Appendix C for the discussion of carbon planets as possible abodes, for silicon-based life. And in fact, we'll get to that, I think, in the next section. Yay, something to look forward to. Oh, now I've forgotten where I was. Excuse me a second. All right, here we go. The discovery of silicon carbide and silicon nitride is surprising in this context. The isotope ratios in the grains suggest that they were formed in oxygen-rich regions of supernova remnants. SiC is thermodynamically disfavored over CO2 and SiO2 in the presence of abundant oxygen, although it is suggested that the grains themselves are oxygen poor. How the oxygen and the silicon became separated is still unknown. And if we can figure that out, then speculating on how that could happen on a planet towards the synthesis of life would be very useful. Because remember, that silicon-oxygen bond is extremely strong. So breaking it up is important, or an environment where that silicon-oxygen bond is not favored. Compounds containing silicon-carbon bonds can also be synthesized naturally under rare terrestrial surface conditions. The authors of footnote 219 The authors have demonstrated the presence of organosilicon compounds in impact glasses called ergesites in the Zamanshin meteorite impact crater. Mass spectrography of the contents of bubbles on the surface of impact glasses shows ions characteristic of polyorganosiloxanes C3H9Si, C5H12OSI2, C7H15O2SI3, etc. Because, as I'm sure you all know, that's a continuation of a series. Organosilane signature ions were less abundant at the mouth of the crater than at the base. Similar ions are not found in Australian strewn field tektites, which are mostly about 0.7 million years old. The authors of whatever 219 is, that's a paper they're referring to, postulate that organosilanes are formed during condensation of the hot vapor created by the impact, which condenses without hydrolysis in the dry environment of the glass particles. Over geologic time, organosilanes are hydrolyzed by water diffusing through the glass. The authors have suggested an equivalent process by which silanes and silanols could be deposited in cryogenic environments. See section 4.1 for the discussion of silicon chemistry and cryosolvents, which I believe we've already covered. And yet that would be interesting I wonder if you could set up a milliurate type experiment for that kind of thing. That would be actually quite fascinating, except for the possibility of the high temperatures. Excuse me, I'm just bringing my clock back up so that I can see where I am. I've actually suggested to my son, given his interest in chemistry, that if one day he ever wants to undertake a PhD in chemistry, this might be an area worth studying. The formation of unsaturated organosilicon compounds. The formation of double-bonded, triple-bonded, or aromatic compounds with silicon is generally highly disfavored and requires special conditions. For example, sterically constrained systems where bulky flanking groups kinetically stabilize the structure. The complete absence of water and often low temperatures are also required. The difficulty of formation and the overall instability of unsaturated silicon systems is in stark contrast to carbon, where double-bonded, triple-bonded, and aromatic systems are formed easily. Therefore, even if theoretically possible, the reactivity of silicon unsaturated systems results in a lot of the chemical space that is normally available to carbon having no direct silicon analogues. The diminished structural chemical diversity of silicon chemistry due to the lack of unsaturated functional groups is not compensated by the fact that silicon forms some unique compounds that do not have stable carbon analogues. For example, penta and hexa-coordinate silicon compounds are stable. Oh grief, how on earth do I pronounce that? Arene diolato bis polypyride silicon 4 complexes contain hexa-coordinate silicon and are surprisingly stable against hydrolysis in water and are investigated as potential DNA binders. Silane diols have been developed as protease inhibitors and are water stable as well. Even if life could exploit such unique chemical functionalities of organosilicon chemistry, it does not provide full functional compensation for the lack of stable unsaturated systems. Thus, at first glance, carbon has more chemical options than silicon, which would be a selection pressure. That is, carbon's more likely to be selected for than silicon. The key differences in multiple bond formation capabilities of both elements are also illustrated by silicon and carbon elemental forms. Both elements form a diamond-like structure, but only carbon is known to form graphene double aromatic bond conjugated systems. The apparent lack of formation of aromatic pi How do I stumble over something like that? The apparent lack of formation of aromatic pi-conjugated systems and double or triple bond connections between atoms is often cited as a severe limitation of silicon chemistry, and the main reason why silicon is not a good candidate as a scaffolding element for life. The formation of such unsaturated organosilicon systems is unlikely at Earth's conditions, that is, 0 to 100 degrees centigrade temperature regime, an abundance of liquid water, and an oxygen-rich atmosphere. However, recent developments in organosilicon synthetic chemistry show that silanes, silicon analogues of hydrocarbons, can undergo a versatile chemistry under conditions that are very different from Earth's environment. Cryogenic conditions, lack of water, no O2. We discuss some such exceptional silicon chemistry briefly below. Even if silanes are generally not known to readily form classical aromatic pi-conjugated systems, a structural analog of benzene was successfully made from silicon atoms. The resulting silicon-benzene analog is not flat like a carbon-based ring, but rather adopts a chair configuration where only the electrons in the central part of the ring are delocalized. This new type of aromatic stabilization, unknown for organic carbon molecules, is called dismutational aromaticity. The same authors suggest that the existence of a fully planar hexasylabenzene might be possible if different substituents or synthetic precursors are used. I am reading here that there is a considerable potential for research into, obviously there's potential for research into this kind of area. Hey, who knows? Maybe my son will get into it. I mean, he is studying at A-level chemistry, mathematics, and computer science, which might position him quite nicely for a career in chemistry. Who knows? It's up to him, however. Hang on. Did I just... Oh, no, I didn't. And this is actually kind of interesting. You can actually see the sort of chair shape here. Recent modern synthetic chemistry approaches were able to uncover synthetic routes to many different unsaturated silicon compounds, not only containing silicon-silicon triple bonds, silicon analogues of alkynes, but also diverse structural motifs containing silicon-silicon double bonds. Some more interesting examples include 1,2 disilobenzene, silicon analogues of allenes, or even silicon-conjugated systems structurally resembling 2-methyl-1,3-butadiene isoprene, a chemical motif widely used by life on Earth. For a very detailed, comprehensive review of recent breakthroughs in organosilicon chemistry, please see footnote 230. I'm not going to be going through all the footnotes, unless someone pays me to, or I get hundreds of comments demanding that I go through the footnotes in this, which seems a trifle unlikely. Unsaturated silicon chemistry is a crucial component of silicon biochemistry and cryosolvents. Under the unlikely assumption that the solubility barriers to silicon chemistry and cryosolvents discussed in section 4.4 are overcome, the unsaturated silicon systems discussed above could be crucial components of silicon biochemistry in the cold. Below, we discuss the potential for silicon unsaturated systems in the context of the crucial biological functionality that they can provide. The existence of unsaturated silicon systems that are direct silicon structural analogues greatly increases the possible diversity of silicon chemistry and the scope of potential biological functionality of silicon-containing molecules. Excuse me a second. I tell you what, this is harder than streaming any video game. Oh boy, even when I have to try and be meaningful, like yesterday when I was streaming Journey. And I do strongly recommend you go and watch that live stream, because the video game itself, Journey, is, I found, one of the more profoundly moving experiences in video games I've ever experienced. Is that a shameless plug? I don't much care. Right. Oh, which reminds me, at some point I'm going to be streaming Flower. I don't know if I can do the whole game, but at some point I'll probably stream Flower, because it came with Journey. Back to silicon biochemistry. Silicon chemistry achieves specific functional goals through compounds with double and triple bonds, such as carbonyl groups, whose silicon analogues have both different properties and are highly unstable. However, in looking for the potential for a silicon-based biochemistry, we need to explore the existence of functional rather than direct structural analogues of terrestrial organic compounds. I think they've actually made this point before. You can't just basically take carbon and substitute silicon. That's not going to work. So you have to look for a functional analog rather than a structural one. The silicon analog of a carboxylic acid may be a silane triol rather than... what? Rather than a silyl carboxylate. Below, we present some speculations on how silicon chemistry could provide fundamental biological functions. Is it just me, or is this going much slower than last time? Oh no, I've only got about 5 pages more to go. Alright. Hopefully we'll get this done. I really don't want to do a third stream going over this. I'd rather find something else. The biological function potentially most affected by the intrinsic limitations of silicon chemistry is capture and delocalization of electronic energy, a biochemical function that unsaturated carbon-based molecules perform quite readily. Therefore, functional biological silicon equivalents of such biochemical processes as photosynthesis and synthesis of a silicon functional analog of ATP are required. If there are no silicon-based functional alternatives, with or without stable unsaturated silicon systems, for such crucial biological functions, then the viability of silicon chemistry as a building block of life looks rather bleak. The solutions to this limitation of silicon were discussed before on several occasions. We summarize and expand on them further. Such complex electronic effects could be performed by unsaturated silicon systems. While they are spectacularly unstable and reactive under water-rich room temperature conditions, their reactivity is much lower in cryogenic conditions. In fact, their reactivity might be just right in cryosolvents. Silicon can form alpha-conjugated polysilanes that have similar electronic properties. That's not an alpha, is it? I'm going to have to look up my Greek alphabet again. I thought that was an alpha. Oh no, that's definitely not an alpha. What is that? Do you know what? I can't find it. Is it? That's not Omicron. It's not pi. Ah, it's sigma. Okay, I should have known. Sorry about that. It's not alpha, it's sigma. Silicon can also form sigma-conjugated polysilanes that can have similar electronic properties to carbon-based molecules containing aromatic pi-conjugated systems. The availability of polysilanes and other silicon-containing compounds to delocalize electrons and have light-activated electronic effects, likely crucial for the development of any kind of photosynthetic system, has been discussed before on several occasions as well. It is clear that organosilicon chemistry is not in any way deficient when it comes to the potential for supporting complex electronic effects, including semiconduction, light activation, and electroluminescence. Another crucial aspect of terrestrial bioenergetics is charge separation chemistry. Earth life uses light energy to separate charge in water, generating oxygen and reducing equivalents, hydrogen associated with a carrier molecule in the process. For example, on Earth, charge is separated in the process of oxidative phosphorylation phosphorylation, which results in proton gradients much larger than single molecules. How can such a charge redistribution occur in very cold cryogenic nonpolar liquids? One possibility is that such charge separation could occur intramolecularly, analogously to the initial photon capture events in terrestrial photosynthesis. Polysilanes are photoconductive due to the ability of light energy to separate charge within the polysilane molecule. Therefore, charge separation chemistry in a protonating solvent is not the only way to capture photon energy in chemical form. Double-bonded silicon systems, for example, silicon structural analogs of ethene, could be utilized as a functional analog of ATP in cryosolvents. Note that proton gradients utilized for ATP synthesis in Earth's biochemistry are uniquely suited to polar solvents like water or possibly ammonia, and are not stable in cryosolvents, and therefore cannot be coupled to the synthesis of cannot be coupled to the synthesis of silicon analogues of ATP. I'm just going to remind myself of what ATP is. I should know, and I've been saying it all this time. Oh, okay. Adenosine triphosphate, ATP. It provides energy to drive and support many processes in living cells. You would, in principle, require an analog for it in silicon biochemistry. Oh, it's also, I forgot this, the ATP Tour is the sole worldwide top-tier tennis tour for men. Yeah, I don't think that's what we're talking about here. I think I'm repeating this, but it doesn't matter. Double-bonded silicon systems, for example, silicon structural analogues of ethene. Oh, wait a minute. Oh, I definitely did go through all that, didn't I? Sorry. Okay. Yeah, I might as well start the paragraph. Double-bonded silicon systems, for example, silicon structural analogues of ethene, could be utilized as a functional analog of ATP in cryosolvents. Note that proton gradients utilized for ATP synthesis in Earth's biochemistry are uniquely suited to polar solvents like water or possibly ammonia and are not stable in cryosolvents and therefore cannot be coupled to the synthesis of silicon analogues of ATP. Silicon double-bond silicon systems, in turn, can be utilized in such conditions as an energy source for the synthesis of countless other molecules. One can speculate that the synthesis of silicon unsaturated systems can be achieved with the help of UV light. For example, one of the approaches used to synthesize carbon-silicon double bonds is by UV photolysis of silanes on ultra-cold matrices, conditions that are not unlike the surface of Triton or Pluto. Similar processes could in principle happen on the surfaces of planets and moons containing liquid nitrogen seas, providing that the ultraviolet output of the parent star at such distance is sufficient. Recall that M dwarfs have less UV output than G dwarfs. All right, you're going to be asking what an M dwarf is. I will look it up. Okay, an M dwarf is apparently a red dwarf and one of the most, in fact, it's the red dwarfs are the most common stars in the universe that we have observed. And what was the other one? What's a G dwarf star? G dwarf stars are... It's a yellow dwarf. There we go. So we're talking red dwarfs and yellow dwarfs. And I'm not referring to the BBC show. Red Dwarf was a BBC TV show, was it not? Yes, BBC Two. My brief divergence into modern culture. I don't know. I don't think that's regarded as modern, seeing as apparently Red Dwarf started airing in 1988. Right, where was I? Such processes could in principle happen on the surface of planets and moons containing liquid N2Cs, providing that the UV output of the parent star is at such distances is significant. Recall that M dwarfs have less UV output than G dwarfs, so recall that red dwarfs have less UV output than G dwarfs. Yellow dwarfs. Actually, isn't our sun a yellow dwarf? Yes, it's a yellow. Our sun is a yellow dwarf. There we go. I thought so. So they're comparing red dwarfs with our sun, basically. You would have to be... Yes. Now the issue with the issue with red dwarfs and this kind of thing is so you'd have to be close enough to get the right amount of ultraviolet radiation, which probably means that your planet is going to be tidally locked, which has its own set of problems because you'd have one side of the planet continuously facing the red dwarf. So one side could become extremely hot, the other side could be extremely cold, and then you have a band around the middle in principle, which would be oh, actually, now that I think about it, depending on if you're talking about cryochemistry, maybe that could occur in the band around it. Because some of that band between the very hot side and the very cold side could receive enough UV light. The authors of this probably know more about that than I do, but there you go. Interesting to speculate. In an analogous way to the highly reactive biochemical systems in Earth's biochemistry, the silicon double bond silicon, it even says, the silicon-silicon double bond can be protected from unwanted reactivity within the cores of complex macromolecular assemblies, allowing for the utilization of the reactivity of the silicon double bond silicon highly energetic bond in a strictly regulated manner. That is double bond, isn't it? Yeah, sorry. I have to move a bit closer to the screen because my eyesight is getting weird as I get older. Appendix D, silicon carbide and carbon planets as potentially suitable environments for suitable biochemistry. Why have they made that a question? That's not a question. The likely conditions where complex silicon biochemistry could potentially prevail can be summarized with the following main points. 1. Scarcity of water to limit the efficiency of transformation of various organosilicon species to the insoluble and unreactive silica. 2. Low temperatures below the freezing point of water to increase the stability of reactive silicon functional groups, like silanes and complex unsaturated silicon systems. 3. The presence of a liquid solvent that is compatible with complex silicon chemistry. 4. The presence of a reducing atmosphere with no O2 to prevent oxidation of reactive silicon functional groups to the chemically unreactive silicon-oxygen bonds in silica. 5. The presence of available silicon precursor components, simple silicon species that are sufficiently reactive to be mobilized and included in the complex chemistry, likely with no dominance of SiO2. It is clear from the list of requirements above that the majority of planetary real estate does not favor silicon-based life. The predominance of silica on the majority of planetary bodies might even make the use of silicon as a heteroatom for carbon-based life unlikely. There is, however, one type of environment, namely carbon planets, that may be more favorable to the use of silicon in biochemistry, a concept that has not previously been discussed. Oh, goody! Carbon planets. I don't know much about them, except I think they're theoretical. In fact, my eyes now just picked up theoretical in the next sentence, but I knew that anyway. Appendix D1, the introduction to carbon planets. I wonder if there are any carbon planets in No Man's Sky. Somehow I think not. There are some planets, I think, which kind of get close to Thermia. That is a sort of molten rock planet. But I haven't explored enough to find out. And in case you're wondering, the No Man's Sky references, because it was a discussion of No Man's Sky with my son that ultimately led to these videos. A carbon planet, or carbide planet, is a theoretical type of planet that contains significant amounts of carbon, much more than a typical rocky, silica-rich planet. The existence of carbon planets was theorized, and the propensity for such exotic worlds is a topic of heated debate. Formation of a carbide planet is controversial, but models suggest that it is more probable with increasing stellar carbon-oxygen ratio and increasing distance from the host star. A number of stars with CO ratios of greater than 0.8 are known. The abundance of such worlds in the galaxy has been questioned on many occasions, but they have not been ruled out. So carbon planets remain an exciting possibility for an environment in which life could, in principle, arise. Important to realize at this point, by the way, the number of stars in the universe, while it's not exactly infinite, is massive. The number of planets in the universe is even more massive than that. The likelihood of a theorized type of star or type of planet is therefore quite significant, even if they might prove to be rare. We have already detected things that I don't think anybody ever really considered. I think the very first extrasolar planet ever discovered was orbiting a neutron star, I want to say. I don't think that had ever been considered. The existence of hot Jupiters, gas giants like our Jupiter, orbiting extremely close to the sun is, I say mind-blowing, but is, we now know those are actually quite common. So there's a lot of stuff out there. So potentially, you come up with a theoretical type of sun, it could exist. All we have to do is try and find it. Same for theoretical types of planets. Thermia, which we discussed last time, was mentioned last time, there is a planet which is possibly like Thermia. So the idea of a carbon planet, they might be extremely rare, but possibly not impossible. Possibly we just need to find it. The composition of the interiors of carbon planets have been modelled extensively. In contrast to Earth, where the great majority of oxygen is bound with silicon to form silicates, the predominant chemical species in Earth's crust, carbon planets are predicted to contain large amounts of carbon monoxide. Carbon monoxide is going to be one of the main sinks responsible for depleting oxygen. The rest of the available carbon, depending on the amount of oxygen, is likely going to be bound with silicon to form silicon oxycarbide, SiOC, silicon carbide, SiC, and titanium carbide, TiC, or will form graphite and diamond layers. The core is mostly built from iron carbides. Depending on the carbon-oxygen ratio, the surfaces of carbon planets can be rich in graphite, other carbon-rich minerals, or hydrocarbons like methane or tar. The atmospheres, if they exist at all, could contain carbon monoxide or methane. Water is likely to be rare, as the reaction of water with carbon, graphite or diamond, to form CO2 and H2 is exothermic and would remove water from volcanic gases. Can carbon planets have favorable conditions for complex silicon chemistry? There are a few characteristics that might make carbon planets a better place for a complex chemistry containing silicon to arise than silicate planets. As we mentioned in the section above, carbon planets likely form further away from their host stars, meaning that they could contain a more diverse collection of solvents on their surface. In particular, the high probability of the formation of HCN, hydrogen cyanide, on the surface or in the atmosphere of carbon planets might make liquid hydrogen cyanide the preferred solvent for complex organosilicon chemistry. HCN, with a liquid range of relatively high temperatures, minus 13 to minus 20, is that minus 13 to? Yeah, that's minus 13 to 26 degrees centigrade. Might provide sufficiently high solubility for biologically active macromolecules. The surfaces of carbon planets are also likely rich in various heavier hydrocarbons like propane or butane. Propane and butane, with their higher boiling points, might also be preferred solvents for the formation of complex silicon-carbon hybrid chemistry. However, carbon planets will probably be devoid of water, one of the most common reactants for silicon chemistry. Any amount of water or other oxygen-containing species that is, for example, delivered via comets or meteors will readily react with carbides on the surface, limiting the sequestration of silicon in the form of unreactive silica. There are, however, some serious limitations to complex silicon chemistry on carbon-rich planets as well. One such limitation is analogous to the sequestration of silicon in silica on water or oxygen-rich rocky planets. As we have mentioned before, one of the main components of carbon atoms is silicon carbide, which can be considered an analog of silica rocks for carbon planets. Silicon carbide is a very strong and hard material, composed of a tetrahedral assembly of carbon and silicon atoms with very strong bonds in the crystal lattice. It is very chemically resistant to both acids and alkali and even molten salts, up to temperatures of 800 degrees centigrade. Thus, mobilizing silicon and carbon from silicon carbide will be very energetically costly. Maybe even more so than breaking silicon-oxygen bonds in silica, and might be prohibitive for life. Yeah, you don't say. The global geological aspects of the durability of silicon carbide rocks can also have detrimental consequences for such potentially crucial phenomena as plate tectonics or rock weathering. Silicates are easily weathered by water, as silica is sparingly soluble in water. Silicon carbide is not soluble in any solvent, so weathering, and hence cycling of elements, would be much more difficult on carbon planets. This might affect their long-term climate and habitability. On the other hand, silicon carbide has unique and potentially beneficial properties as an exceptional support for various metal catalysts. Silicon carbide is often used in industry for catalysis of chemical reactions like oxidation of hydrocarbons such as N-butane to maleic anhydride. Involvement of silicon carbide in the catalysis of various chemical reactions might help in the facilitation of the formation of complex chemistry on carbon planets. It is also likely that not all silicon and not all carbon are going to be locked in silicon carbide rocks. For example, silanes will be stable in the majority of conditions on carbon planets. If the abundance and diversity of silicon-carbon compounds in the interstellar medium is any indication, then we could expect in principle a diverse collection of silicon-carbon building blocks for biochemistry, even if they exist on a largely chemically inert but catalytically active silicon carbide surface. For perspective, the vast majority of iron on Earth is locked in the Earth's core, but this does not mean that trace iron cannot be a key part of terrestrial metabolism. And I suppose you could point out to the presence of iron in our blood, for example, in hemoglobin. How much further have I got to go? Well, it says here page 33 of 47. I'm not going to go through the references. So in principle, I've only got 3 pages to go. What time is it? I've already been doing this for an hour and a half. I sincerely hope I can finish in the next 15 minutes. Maybe if I stop going off on irrelevant tangents. Appendix E. Chemical diversity, thermodynamics, and solubility calculations. Appendix E1. Chemical diversity calculations with combimol B. Theoretical chemical structures were generated by the program combimol B, which is based on the concepts implanted in the original combimol as described in footnote 33. Combimol B operates as follows. Okay, I've got to check on what combimol combimol B. Let's see if we can find a combim. I can't spell. I can't find it. Did I spell that correctly? Combimol. I'm now going to mutter to myself. Yes, here we go. Combimol B is a program that generates a set of all possible chemicals that can be built from a defined set of atoms, bonds, and molecular topologies that can be used for non-commercial purposes. Okay. Yep, it is what they say. Well, obviously it is what they say. I was just interested in finding out a little bit more. As input, combimol B, I don't suppose you can find that on Steam, can you? Combimol B takes an alkane structure which defines the topology of atoms. A new alkane is therefore needed for each topology, and an increasing number are needed for each size class of molecule. For convenience, the notation N equals is used to describe molecules with N non-hydrogen atoms in them. Thus, for N equals 2, the input is ethane. For N equals 3, the input is propane and cyclopropane. For N equals 4, the input is butane, isobutane, methocycloprotane, and cyclobutane, and so on. The program is provided with a list of atoms, a list of bonding rules for those atoms, and a list of rules for which bonds can form between those atoms. You know, I can just imagine some YouTube channel dedicated to playing around with combimol B. No, don't look at me. It's probably beyond me. Thus, for phosphorus, the program might state that is... Oh, okay. Thus, for phosphorus, the program might state that it must be bonded to between 1 and 3 atoms, and that it can be bonded to carbon but not to chlorine, thus implicitly stating that phosphorus-chlorine bonds are unstable, as they are in water. The bonding rules and atom lists are user-defined. Using these rules, the program recursively replaces all the atoms in the molecule with atoms from the input list as follows. First, the single bonds between input carbons are replaced systematically with double or triple bonds. Specific rules prevent triple bonds in rings. A user-defined switch in the program can select whether to accept cumulene structures, carbon, 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 double bonds between each. In the execution used for this work, cumulenes were accepted. Cumulenes are not allowed in rings. The exclusion of alkynes and cumulenes from rings is pragmatic, based on the small size of the molecules being generated, to avoid structures such as psychoprop 1,2-diene. Is that C1 or chlorine? C1 carbon C1, which are implausible. I need a new pair of glasses. I need bifocals. For each of these hydrocarbon cores, the program recursively substitutes carbons for other atoms in the list according to the rules of bonding provided in the 2 files, which specify which atom can be joined to which and which atom can support double or triple bonds. Thus, if the input structure was ethane and the atom list was nitrogen and the oxygen, the program would generate structures whose SMILES description... What's a SMILES description? I have a feeling I'm not going to find it. No, I'm not. A smile is if... Yes, I know what a smile is. I just don't know what it is within this context. It's obviously an acronym. The program would generate structures whose SMILES description would be carbon, carbon, carbon double bond, carbon, carbon... I think that's supposed to be triple bond. Carbon monoxide, carbon double bond oxygen, carbon nitrogen, carbon nitrogen, carbon... Okay, I don't know what the current nomenclature is for that, but yeah, I'll leave you to to read it. I really don't know how to narrate that properly, assuming I've gotten anything vaguely right so far. If bonds between nitrogen and oxygen were not allowed, then NO and N double N double O no, and N double bond oxygen would not be generated. If nitrogen was specified not to be able to support double bonds, then nitrogen with double bond molecules would not be generated. The program also filters out chains of non-carbon atoms. While nitrogen can be singularly bonded to nitrogen, as in hydrazine, the structure N is never found in any stable molecule. That, by the way, would be equivalent to using nitrogen as a structural atom in the same way that carbon can be. And I should also point out that hydrazine, I think, is really, really unpleasantly reactive. Several specific rules, mostly user-defined, implement these filters. Duplicate molecules are identified and removed via their, whatever that is, INCHL code, INCH1 code, INCHI code. Some molecules cannot be generated this way, such as nitric oxide, which violates classical bonding rules. However, these are a relatively small fraction of all possible molecules. Some, which are plausible on classical bonding terms, such as nitrogen double bonded to oxygen, are actually not realistic. Come on, I've only been going for 100 minutes. Pentavalent atoms cannot be accommodated in this process, and so to accommodate pentavalent phosphorus and arsenic and hexavalent sulfur, specific atom types are predefined in the program. These are listed below, separately from sulfur and phosphorus, which are assumed to be S2 and phosphorus 3, respectively. By the way, when I said S2, that's sulfur type 2, not a molecule S2, which, as far as I know, doesn't exist. And those occur, I think, under various heating conditions. You may be familiar with the fact that if you heat up sulfur, you get different colors of sulfur, and I think something similar happens with phosphorus. For example, you can get red phosphorus and white phosphorus. If you look at the moon of Io, Io is this beautiful moon in our solar system, and a lot of the colors that we see on the surface are from different forms of sulfur. For this exercise, it says here, for this exercise, 2 sets of staring alkenes were used. Is that supposed to be 2 sets of staring alkenes, or 2 sets of starting alkenes were used? For the aprotic solvent, an exhaustive set of alkenes of N2 through N7 was used, including rings and fused ring systems. For the water and sulfuric acid solvent set, only 5 and 6 and 7 membered rings were used. 3 and 4 membered hydrocarbon rings, in which one or more carbon has been substituted with a silicon, are highly reactive, reacting explosively with acid. For example, the aprotic solvent was assumed to be a cryogenic solvent, like liquid nitrogen, which allows for the formation of many bonds. The only phosphorus species allowed in sulfuric acid are phosphonium groups, as phosphate and thiophosphate esters are rapidly hydrolyzed, and phosphines are oxidized by sulfuric acid. Silicon is defined in water as requiring 4 bonds, that is, silicon-hydrogen bonds. The default, if no other element is specified, are not allowed. In sulfuric acid, SiH bonds are allowed. Bonds defined for the 3 sets of solvents are shown in Table A1. Bonds not allowed in each solvent are ones which are broadly liable to hydrolyze in those solvents. The filtering of structures for stability is only partially effective, but as the overestimation of the size of the chemical space is likely to be the same for all sets of molecules generated, the filtering approach can be used to compare the extent of the subsets of chemical space that reflect the stability and reactivity of chemicals in different solvents. The Combimol B PC executable source code and documentation and some example input and configuration files are available from WB on request. The program is written in QB64 BASIC. Sorry, I shouldn't laugh. That's slightly amusing. I have no idea what QB64 BASIC is like. I mean, what BASIC is, obviously. What is Keyboard 50C? I wonder if it's a compiled BASIC. Oh, it's a modded It's a modern extended basic programming language and actually has its own web page and is available for Windows, Linux, and Mac OS. Huh. Wow. Well, that's interesting. Huh. It's interesting. That's all I can say. I don't know to what extent this is still true, but in the scientific world, I mean, when I was a student, I worked briefly for a pharmaceutical company, and Fortran was still being used there. In fact, one of my tasks was converting Fortran programs to DEC basic programs, which was more up to date and more modern. And the whole point of that was to make absolutely sure that the output from the Fortran programs matched precisely the output from the basic programs. Trying to remember the name of the company. It was a big one. What was the name of it? I can't remember right now. It was a long time ago. That was nearly 40 years ago. Yes, I don't know how to narrate that at all. Oh my goodness, I don't know how I'm going to narrate this either. I'm going to have to hope. Oh, we're almost done. Huh. All right, this is the last page I think I need to read. And I'm afraid this is going to end on a bit of a down note, because that's the end. Those are all the references in this work, and this is the last of the narratable text. And I'm not sure what conclusion can be reached from this. Appendix E2, Thermodynamics of the Formation of Silicon Compounds. List of chemical reactions considered in calculations of the thermodynamics of formation of silicon compounds. Yeah, okay. And I can't remember what the X represents there. I'm sorry, I can't. Appendix E3. Yeah, I'm almost finished, Thivia. Appendix E3, Estimation of the solubility of silicon chemicals in liquid nitrogen. For some reason, I thought there was, in fact, a conclusion to this. So I'm going to have to probably make that up in a few minutes. We used the Abraham model to predict the solubility of silicon chemicals in liquid nitrogen. The Abraham models predict the log of solubility as the weighted sum of the excess molar refraction, induced dipole polarizability, McGowan characteristic volume, and 2 hydrogen bonding factors. This is almost meaningless for me to read out, to be quite honest with you. I am therefore going to completely skip this. I can't read that with any particular meaningful. I can't even make it vaguely sound meaningful. So we're basically all pretty much at an end. And it has to be said that is a really unsatisfactory ending, for which I am so sorry. Um, okay, so if I were to try and summarize this, what is if someone were now to come to me and say, what is the potential of silicon as a building block of life? I would then turn around and say, okay, maybe. I think that's the simplest. It's if you have the right set of circumstances, which do not seem to be too likely to occur, then maybe. But given the size of the universe, it's I would honestly. All right, if someone were to ask me the question, do I think that there is life elsewhere in the universe? The simple answer to that question, of course, there is. What we know about life on Earth means that it's almost inevitable elsewhere it is inevitable elsewhere in the universe. It's probably highly likely simply elsewhere in this solar system. When you look at the sheer immensity of the universe, the sheer number of galaxies, the massive number of stars and planets, is there life there? Of course there is, yes. Is it likely to be what kind of life? Well, microbial is extremely likely. You can almost make that prediction based on the fact that for something like 80% of the existence, in the time that there has been life on planet Earth, for 80% of that time it was single-celled. Which may be a startling realization to some, but nonetheless it appears to be true. We also know that it started very easily. The Earth is about 4.5 billion years old, and the earliest life dates back to between 4.2 and 3.8 billion years. So therefore it seems that almost as soon as it was possible, life got started on this planet. And one can extrapolate from that to say, well, based on what we know about Earth, the likelihood of life elsewhere approaches 100%. Intelligent life? Don't know. I would be surprised if we were the only intelligent life in the galaxy, let alone the universe. Now that discussion gets, much more complicated. So, is it possible that there is life that is not carbon-based? Given the immensity of the universe, you could say, well, based on this paper, they've basically laid out, here's a series of circumstances, here's some possibilities. It doesn't seem impossible. Unlikely, but not necessarily impossible. And I am now probably showing my ignorance, we have to kind of bear in mind that what we know about life is primarily based on carbon-based life forms. Obviously, that's all we know. Remember that Carl Sagan said that he was a carbon chauvinist. That's not an unreasonable position to take. This paper is essentially saying, right, we know that life requires complex chemistry. What can we do with complex chemistry and silicon? It's quite reasonable. Is it? And they address: is it possible that there could be? What was it? The two that I remember: silicon and boron. Of the two, silicon can form long chains or large molecules, and boron tends not to. Is it possible that there is some other form of chemistry that we simply have not considered because it is so alien to us? I am inclined to say I don't know. It Yes, at this point I start spluttering and saying, having to admit I don't know. So there's sort of two answers to this question. The first answer is, yeah, maybe, and the second answer is, no, not likely. But not likely does not mean impossible. Right, I think that's me and my voice and my throat done for today. I hope anybody watching it enjoyed it, or at least found some relief from their insomnia as a result. And I do intend to do more streams based on science that I am inspired by in video games. I've also got a few other ideas that I shall have to check into, and we'll see how this goes. I hope that you all have a good day, and I won't see you later, but you'll see me later.